Hello, this is Dr. Brown. In this video, we're going to talk about applied optimization, and we're going to look at how some of the techniques we've learned on maximizing and minimizing functions will help us, say, in various applications, design a manufacturing technique that will maximize something or minimize something, like maximizing your revenue or minimizing the cost, maximizing volume, and doing all kinds of things in the real world. In the first example here, we have a piece of metal that's 24 inches by 24 inches, and we want to use it to form a box for shipping that we'd like to have maximum volume. And as you can see, what we're going to do is cut out X inches along the dotted lines here from each corner, and then turn up the flaps so that we form a box that looks like the figure on the right. And now the dimensions of the length and the width will be 24 minus 2x, 24 minus 2x, because we've taken x inches out of each corner. And of course the height of the box will be h, and of course the volume is a length times a width times a height. So the volume that we're going to produce will be the height, which is x, times the width, which is 24 minus 2x, times the length, which is 24 minus 2x. And this is going to be x times foiling it 576 minus 96x plus 4x squared, and then distributing the x, we get a volume of 576x minus 96x squared plus 4x cubed. And then we want to take the first derivative of the volume, and we find that the first derivative of the volume is 576 minus 192x plus 12x squared, and we want to set that equal to 0 and find the critical points. Now factoring this and start this off with a leading x, we get, and factoring a 12 out, we get 12 times x squared minus 16x plus 48, which factors into 12 times x minus 12 times x minus 4. If that equals 0, then the critical values are x equal 4 and x equal 12. And notice that the x equal 12, which is a critical point, is also an end point, because we can't take any more than 12 inches out of each corner. That would be the limit. Otherwise, the length and the width would be negative. So this is a critical value, and it's also an end point. notice that the volume at x equal 12 is equal to 0. That would give you no box. If you took the other endpoint, which was x equals 0, the volume at 0 would be 0. So the endpoints give you 0 volume. So we need to check the other critical value, which is x equals 4. And the volume at x equals 4 is just 4 times 16 times 16 equals 1024 cubic inches. And that would be the optimal volume for the optimal value of x, which is 4 inches. On the next page, you can see the volume versus x, and you can see at x equals 4, the maximum is 1024 cubic inches. Now, we have a manufacturing problem here that says that x cubed minus 18x squared plus 30,000x is the cost of manufacturing x items. What production level will minimize the average cost per item of making x items? Well, the average cost, if we let A equal the average cost, this would be the total cost, which is x cubed minus 18x squared plus 30,000x divided by the total number that you are manufacturing, which would be x. This would be the average cost, and you can see this is equal to x squared minus 18x plus 30,000. So if we take dA dx equal a prime, the first derivative we get 2x minus 18, and we set that equal to 0, and we get 2x equal 18, and then x equal 9. So we want to manufacture 9 items. Now the next example is to find two numbers x and y such that their sum is 60 and that x squared times y is a maximum. So we want to maximize, let's call it a variable w equal x squared y, and the constraint that x plus y is equal to 60. So we can solve for y and say that y is equal to 60 minus x, and this will allow us to substitute y into the first equation so that we will have only a function of x. Notice that right now we don't know how to take a derivative of a function that has more than one variable. So to reduce the number of variables and to complete the solution, we substitute y equals 60 minus x. And so now we get that w, which is a function we want to maximize, is going to be 60x squared minus x cubed. And now we take dw dx equal w prime is 120 x minus 3x squared equals 0. And factoring, we get x onto 120 minus 3x equals 0. And we get that x equals 0 and x equal 40. Notice that x equals 0 gives us 0 for w, but for x equal 40, w is going to be x squared, which is 1600. Times y, which is 60 minus x, which is 40. And that makes y equal 20. So the two numbers are going to be 40 and 20. And the W max is going to be 1600 times 20, which is 32,000. So the two numbers that we pick are 40 and 20. Now the next problem is one in which we want to maximize a profit in a manufacturing operation. The revenue when X thousand units are manufactured is given by R of X equal 10X, and the cost of manufacturing X units is given by C of X equal X cubed minus 9X squared plus 25X. And the question is, how many units should be manufactured to maximize the profits? So we're going to be manufacturing X units where X is in thousands, and the profit that we obtain we call P of X, and obviously it's going to be the revenue, how much you sell all of these products for, minus the cost, and that will be 10x minus the cost, which is x cubed minus 9x squared plus 25x, and this is equal to 10x minus x cubed plus 9x squared minus 25x, and simplifying we get minus 15x minus x cubed plus 9x squared. So now we want to take the first derivative of P and find the critical values. And the first derivative of P is going to be minus 15 minus 3x squared plus 18x. And we're going to set this equal to 0. And turning this around and multiplying P prime by minus 1, we get 3x squared minus 18x plus 15 equals 0. Factoring out a 3, we get 3 times x squared minus 6x plus 5 equal 3 times, factoring the quadratic, we get 3 times x minus 5 times x minus 1 equals 0, and we get that the critical values are x equal 1 and x equal 5. Now we want to evaluate these critical values, and we can use the second derivative theorem. So let's take the second derivative of p to find out whether these are relative min or relative max, and we get the second derivative is equal to minus 6x plus 18, plus 18. And we need to evaluate the second derivative at x equal 1, and we get minus 6 plus 18. And that is more than 0. That means it's concave up. So this is a relative minimum, and that would actually minimize our profits. Then the second derivative at 5, plugging in, we get minus 30 plus 18. It's less than 0, so it's concave down. So that's the relative max. And so the maximum profit would occur if we manufacture 5,000 units. And we can calculate that in the original equation, and plugging in 5, we get minus 15 times 5 minus 5 cubed plus 9 times 5 squared equals 25. So the profit is 25, and by the way, this is in millions, so we would make $25 million profit if we manufacture 5,000 units. Now, if we manufactured x equal 1, which would correspond to manufacturing just 1,000 units, notice we would have a profit of minus 15 minus 1 plus 9, which is minus $7 million. So this would actually be a loss of $7 million. Notice that this is illustrated on the next page, where we have the profit in millions of dollars versus the number of units manufactured in thousands. And you can see that at 5,000 units, we make $25 million profit. If we had manufactured only x equal 1 or 1,000 units, we would have a loss. Now the next problem is we want to make a trough that has the end dimensions shown below, and the length of the trough is to be 24 feet long. We want to know the value of theta, that's this angle here, which will give the maximum volume. So the volume will be the area of the end piece times the length, which is 24 times the area of the end. So now the area of the end, in order to figure that out, we need to figure the area of this trapezoid. Notice that we need to assign some variables here. Let this length be x, and let this length be y. And notice that x divided by 1 is equal to sine of theta, and y divided by 1 is equal to cosine of theta. So the area of the left and the right triangle would be 1/2 the base, which is y, times the height, which is x, which is 1/2 cosine of theta times sine of theta. So make that a little clearer. It's going to be 1/2 cosine of theta times sine of theta. So the total area of the end, which we'll call A, is going to be 2 of the triangles, which would be cosine of theta times sine of theta, plus the area of the rectangle, which is this rectangle, which is going to be 1 times y, and this is going to be just cosine of theta. So this is the area, and we want to now calculate d80 theta, which is A prime. We now have to use the product rule, which is going to be the first, which is cosine of theta, times the derivative of the second, which is cosine of theta, plus the second, which is sine of theta, times the derivative of the first, which is minus sine of theta, plus the derivative of cosine of theta, which is minus sine of theta. And we want to set all that equal to 0. So now A prime is equal to cosine square theta minus sine square theta minus sine of theta. And we want to set that equal to 0, so we've got a quadratic trig function. Now, notice, you'll remember that sine square theta plus cosine square theta equals 1. So cosine square theta is equal to 1 minus sine square theta. we want to get rid of either the cosine or the sine, and the easiest way to do it is get rid of cosine square. So cosine square theta is equal to 1 minus sine square theta minus sine square theta minus sine of theta equals 0. So combining all of this, we get 1 minus 2 sine square theta minus sine theta equals 0. Turning this around, we get 2 sine square theta plus sine theta minus 1 equals 0. So what we need to do is factor this, and we notice the factors would be 2 sine of theta minus 1 times sine of theta plus 1 equals 0, and we get sine of theta equals 1/2 and sine of theta equal minus 1 are the critical values. So that the sine of theta equals 1/2, looking at your unit circle, theta would be equal to 30 degrees. For sine of theta equal minus 1, theta would be equal to minus 90 degrees. And obviously you wouldn't have a trough, so this is no solution. So the optimal angle will be theta equals 30 degrees. Now, the last problem we're going to do is we're going to build a horse pen to be built that's made up of 2 connected pins. The right pin is to be twice as wide as the left pin. You have only 1,800 feet of fencing available. So what should be the overall dimensions of the pin so the area is maximum? Notice that the constraint is you only have 1,800 feet of fencing. Let's look at the total amount of fencing you need if you call the left pin, let it have a length of x or a width of x, and the right pin a width of 2x, and let the height of the pin be y. The total length of all the fencing is going to be 1x plus 2x plus 1x plus 2x, which is 6x, and then the plus 3y would be the 3 vertical sides. 6x plus 3y is going to be equal to 1,800, and we'll have 3y then is equal to 1,800 minus 6x. So y is equal to 600 minus 2x. So that is going to be a constraint, and we want to maximize the area. Well, the area is going to be xy, which is this area, plus 2xy. So the area is going to be 3xy, and substituting for y, which is 600 minus 2x, we get that the area of the total pin is going to be 1,800 x minus 6x squared. To maximize this, we want to take the first derivative, which is 1800 minus 12x, set it to 0, and so we get 12x equal 1800, and x is equal to 150. The y that corresponds to that will be 600 minus 2 times 150 is equal to 300. So y is 300, and x is 150. So 2x is 300. So the total width will be 450 feet, and the height is going to be 300 feet. So the dimensions will be 450 feet by 300 feet to give the maximum area. The last thing I would like to mention before we end this video is to just look at a practical situation. And the practical situation, this is not in your textbook, but we're talking here about the concept of robust optimization. Suppose you had to design some kind of power plant that was generating so many watts of power, and you had a controlled set point that could be varied between 0 and 100, and the power output function looked like this, and you wanted to maximize the power output. If you looked at just finding the absolute max, you would pick x equal 20, and you would get a maximum of 9 watts out. Notice that there is another local minimum that if you set the point at 85, you would get about 6.8 watts out, not as much as the 9 watts. But suppose you could not always set your set point exactly at the prescribed value. In other words, it could only be, say, plus or minus 2 set points away from the optimal setting. Then notice if you had picked 20 and could only go 20 plus or minus 2, if you deviated 2 away from the optimal, you would get an output of just a little over 2 watts. If you deviated the other direction, you'd have just a little over 2 watts. And you might have a requirement that the watts not drop below, say, 6. So you'd be in real trouble if you went for the optimal and couldn't quite set it. But notice if you went for what we call a suboptimal amount and picked a set point of 85 and could vary at 85 plus or minus 2, you would still have a very comfortable output that is above the required 6. So sometimes you might not go for the absolute max if you could not set your system up to always run at the optimal value. You might want to do what we call a robust optimization and take a second, possibly just relative maximum. and that's the video.